Hello and welcome to the module Robot Statics. We are now ready with sufficient background on structure of the robot and its kinematics, both forward and inverse. We have covered it in earlier modules. We have now calibrated the robot and its peripherals to do any task. We now know how is it installed and put to any application after installation. So let us now gradually start moving the robot to do any task. To begin with, let us understand some static and quasi-static tasks and its mechanics. So before we begin, let us quickly summarize the contents that I will be covering in this module. So yes, statics as such is a branch of mechanics that deals with forces and torques acting on any physical system that is in equilibrium with its environment. So this is an age-old definition of statics. So when it comes to robotics, it is no more different. It is very much the same, only the source of forces are different. However, we are not going to study the source of force when we do statics. So where from those forces are coming? Mostly they are due to the interaction forces, what the robot can encounter while it is performing any task, or due to its own masses or whatever load that it is carrying, or whatever task if it is doing. So without considering any acceleration forces and dynamic forces, so we'll study the robot in this particular module. Okay. So yes, to begin with, links and joint forces and moments. A recursive approach that I'll be using, that is quicker and more reliable and faster when it comes to applying those algorithms to find out the link and joint forces and moments. Okay, few of the applications, they include design of the robot links and joints. If at all you are intending to design any robot, you should be familiar with the mechanics that actually goes in when you have to calculate the links, what are the forces that is going to come on it, so that you can put to boundary conditions well when you actually go and analyze those links, whether it will fail or it won't fail. Okay, so this is very much useful in doing so. Controller design for precise manipulation. If at all you have knowledge of forces what are going to come, even if when the robot is static, it is not moving. So we'll see very much in detail how that is used. Okay, these kind of mechanics that we are going to do today will be used in controller design, actuator selection, transmission design. All these requires knowledge of link, joint forces and moments. So that we'll be doing in first lecture of this module. Next lecture I will be covering gravity compensation, handling external forces and moments while performing any task. If at all it encounters any sort of interaction with the environment, so what kind of forces and moments and torques that is going to come in its joint, so that you can have sufficient torques through the actuator developed so that you can handle the task. So that is all we'll be covering in this module. Okay, and particularly in this lecture we'll look upon gravity compensation. So that is second one. Force and velocity ellipsoids, estimating the maximum velocity and force a robot can generate in any configuration. Okay, and different directions, how much force it can apply, different directions, how much velocity it can go, whether this is maximum or that is. So we'll have a particular relation between them. Okay, performance analysis, planning for a task execution, all these will require knowledge of force and velocity ellipsoids. So with this we'll start today's lecture, that is link and joint forces and moments. So let us begin. So yes, before we start with links, forces and moments, let us formalize a link. How does it look like? An isolated link is drawn here. Okay, so you see this is a link, this one, ith link, any link, 1, 2, 3, 4, 5 till n. So whatever is the number of links you have, any one of the link, if you extract it out, so it is acted upon by the forces and moments by a link which is prior to this as well as from the link which is coming after this. So it has all those. So let me just start with the moment which is here. So you see this one. This is the moment that acts at OI, that is the frame which is attached to the joint I, bottom of that. So about this joint, this link is able to rotate. You know that already. So this is your OI on which this moment is acting on. So it comes at the one end of the link, that is this end of the link, from the link which is attached before to this. Okay. And then this is your force Fi minus 1 I. This was Ni minus 1 I. So moment acted upon by I minus 1th link to the ith link. That is what is meant by this. This is xi, that is the axis of this link. And that is the coordinate system which is attached over here. Okay. And then a similar end exists at the other end of this link. So this is this point which is OI plus 1. That is the frame which is attached to the end of this link. Okay. You have another link that comes after this that can rotate like this. Rotate or translate whatever it is. So this is also acted upon by a reaction force by the link which comes after this. So you have an II plus 1. So if this link delivers a moment II plus 1 to that, so negative of that will come on it also. Same with the force. So it is minus Fi I plus 1 that comes on this link by the next link. Okay. And you have something which is here, that is Ci. What is that? That is the center of mass location of this link. Okay. Mi is the mass of that link I. Okay. These we already know. This is over here. These two comes over here. G is acceleration due to gravity, and it is represented in the base frame, which is aligned with the world frame which is here. Okay. Di is the position of center of mass of the ith link Ci relative to the origin of ith frame OI. This is virtually constant because with respect to OI, CII is not going to change. As long as robot is assembled and it retains its structure, so that CI location with respect to OI is not going to change. So this is here. Okay, and similar is your Ri, position of the I plus 1th frame, origin OI plus 1, that is this one from Ci, relative to the center of mass of the link I, that is Ci location. Again it is constant because the structure is no more changing once it is assembled. So this is also constant. Minded, the frames are different in which both of them are represented. So Ri is represented in this frame, whereas Di is represented in this frame. Sum of the vectors, if it is in same frame, should result in Ai. What is that? Ai is position of the OI plus 1th frame, this frame, with respect to OI. Okay. So that is the position vector that connects both of them. Okay. So Di plus Ri effectively should be equal to Ai if Ri is also expressed in OI frame. Done. And there is one more thing to it, that is Qi vector, that is rotation matrix transforming the vector representation in the I plus 1th frame to the ith frame. So it is nothing but an extract of rotation matrix that comes out of the link transformation matrix. You have studied well while you were studying DH parameters and link joint parameters. Okay. So you know the transformation matrix that takes you from OI to OI plus 1. Okay. So that rotation matrix that exists, 3 cross 3 rotation matrix that exists as a part of that is Qi. So it will take the orientation change from this frame OI to OI plus 1. Okay, so these are some of the notations that I'll be using when I'll do the analysis of this. So let us quickly see what are the forces and moment balance equations that exist. So overall, I am going to study the statics of it. So what I should see is this link should be in equilibrium condition, provided it is acted by the forces from the input and the output side of it. So these two forces which are acting over here, moment and force, same over here you have a moment and a force, and additionally you have a force that is due to the gravitational pull at the center of mass of this link. So all these forces should make it in equilibrium. Okay, so the force balance equation should be, so Fi minus 1 I, so that is this one, okay, minus Fi I plus 1, it is negative symbol because it is acted upon by as a reaction force, that is this link itself is applying to the next link. So as a reaction it sees a negative force, and Mig that acts downward along the axis of G. Okay, so that comes here. So sum of all those forces should be equal to 0. Mind it, this is not just 0, it is a 0 vector. So this is a 3 cross 1 vector, this is 3 cross 1, this is 3 cross 1, same as this one also. Okay, so that is force balance equation. Similar will be your moment balance equation also. So you have a moment that comes from this end of it, you have another moment that comes from here, okay, and there are moments which are created due to the forces also. So that is nothing but this one, Ei, that is this vector, and the force that comes here, that is over here with a negative sign. Okay, similarly you have Di and this force which is here, Di and force, that will be positive, and again it is a 0 vector. Okay, so you have sum of all the moments is equal to 0. So this basically defines the equilibrium condition. Let us name it as 1 and 2, that will be referring later also. So this is your forces and moment balance equation. So this is the only set of forces and moments that comes on this link and makes this link static in the space. So this is nothing but just like a free body diagram in space. Okay, okay. So now let us just rearrange the force and moment balance equation as we just saw. So I am expressing the force that comes here in terms of force that is here. So if you know this one, you know this one, plus this will come in between. So you see what I am trying to do, I am trying to create a chain sort of thing, okay, so that I can do some iteration or that kind of thing. Will come more precisely later now. Okay, similarly Ni minus 1 I, this one is equal to, you have a moment which comes here and moment that are created due to the forces. So one of the force is over here, okay, so that is this and this. Again you have another moment that is created due to Mig, okay, with Di. So that is all. So you have expressed the same 1 and 2 equations in this form. Okay, so in terms of dH parameters, you can write Ai. Ai, how do you see here, is a link length. What was that? It was the shortest distance between, a perpendicular distance between y and I plus 1. So if at all you are able to draw something like this, so you should see something like this, and there is a perpendicular offset also that was existing, okay, that is from along Zi starting from y. So that is your Bi, that is also there. So if at all this link makes an angle theta I from here, so you see you can write Ai in ith frame as Ai cos theta, Ai sin theta and Bi. So that is what are the three offsets that you see from your origin OI that creates the position vector Ai in ith frame. Okay, so that is how it is written. Next is your closed vector triangle, that is made out of Di, which is in ith frame already. Ri in ith frame, it is nothing but Rx, Ry and Rz. Let us say these are the three components which are there for this Ri. This is a known vector. You know the center of gravity location with respect to OI plus 1th frame. Okay. This is your Ai in ith frame. So D plus R gives you A. So it can be written like this. Okay. Quite trivial. Additionally, what I have here is Qi. Why? Qi is nothing but as orientation transformation that takes you from OI to OI plus 1. Because Ri was written in the frame OI plus 1, okay, so I have to transfer this, the same vector with the same magnitude in OI frame. Okay, so that is the reason why I am multiplying with Qi. So that makes everything in the same frame, that is the ith frame. So this is how it is finally written in ith frame. Okay, so now let us start recursively computing the link forces and moments. Okay, so the joint reaction moment forces can be computed by backward recursion. Okay, starting from the last link where the end effector is mounted. So what is known, fully known, is everything we know about the end effector. We know how much is the mass of this end effector. We know the gravity g direction with respect to this also. So we can quickly calculate how much will be the force that this end effector is applying on the nth link. That is the last link. Okay, so we have all the information about this end effector. Okay, so that is what will be used. So starting from this, we know what this is applying here. We know the link mass and center of gravity location for this also. So now this end is calculated. Whatever force and moment that is going to come here will be calculated. Okay, so that is how we'll go backward like this. Okay, we'll start from here, which is fully known. We know nothing is attached after this, and we know everything about this link. So we start from this one. Okay, and then we'll go back. Okay, so that is the reason why I wrote the force and moment balance equation in backward manner. Okay, so the end effector moment n plus 1 n is equal to minus of n plus 1, is it not? So it is reverse way. Whatever this applies forces and moments to this applies in a reverse manner. So that is what it is, nothing but action reaction pair. Okay, for the force and the moment both, that is known in its own frame. Okay, for the last link it is always known, we know 100% of it. For this link, you know this is always true, action and reaction pair, they balance, only the directions are inverted. Okay, and then the reaction for force n minus 1 n, that is over here, and the moment at the nth joint, which is here, is calculated using equations 1 and 2. Okay, if you know what is going to come here, you already have information of center of mass location and its own mass, so you now can calculate this one using equations 1 and 2 as we have seen. Let me just show you once again this one. So these are the two equations. If you know mass and center of gravity location, you know this, you already know this, so you can calculate this in backward manner. Same for this. That is what is done here. Okay, okay, so you have now used these two equations to find out what are joint force and moment that is going to come here. Okay, the process is iterated backward now from I is equal to, you started with end effector, you did first for the nth link, then you do for the n minus 1, n minus 2 and so on so forth in a backward manner till the first link. Okay, until all the reaction moments and forces are found, is it not? So you have full information about this. Using this, and the mass moment is calculated from Cn location, and that is added over here. Finally you got everything over here. Then you proceeded backward. Again, for this link, you know now this one, you know this center of mass location and its values. You can calculate here. You proceeded everything in the backward manner from this to this. You got it? So this is how it moves in backward iteration. Okay, so equation 1 and 2 for the ith link are first written in the I plus 1th frame. So if it is any I link, so you have to write everything over here so that you can do all the vector sum that comes from this side of it. Okay, so you have expressed everything over here. Okay, so whatever equation 1 and 2 you have for the force and moment backward iteration formula that we have written over in equation 1 and 2, so both of them are expressed in I plus 1th frame. Okay, same for the moment, same for the force. You do all sorts of vector addition, subtraction and balance over here. Okay, and then you transfer that to this location. Okay, you transfer that to this location. How? Using the link transformation matrix, that is the orientation change that is happening from here to here. Okay, so once the reaction forces and moments are computed in I plus 1th frame, that is over here, they are converted to the ith frame. I bring all the forces and moments to this frame. Okay, and then I'll handle the link which comes over here. So again, all the forces and moments will be expressed here. Do everything and bring it here. Likewise, so you have to keep moving backward. Okay, so because you know all the vectors and moments can only be added if they are in the same frame. So this is why this value is used. You know Qi for all the links, okay, through your DH parameters. Again, as G is specified, you know G, it is always specified in the ground fixed frame, that is the world frame or the first frame of the robot which is attached to the ground. So that is fixed to the frame 1. So that also needs to be converted to the link frame using this. Gi plus 1 and I will again be related to this using Qi. So if you know G in this frame, so in this frame you have to convert it back. Okay, so again it has to be converted one by one from one frame to the other, like this. Okay, you have to keep moving backwards again. So whenever you consider this frame, G should be expressed in this frame. When you consider this frame, G should be converted to this frame. So whatever, again G also should be compatible to be added and subtracted. Okay, so everything should be in the same frame. Okay, so that is the reason I am using this, and Qi is well known. This is nothing but Qi transpose. What does it say? It is Qi. It is a rotation matrix. So instead of taking inverse, I can quickly find it out by taking transpose of this. You know, rotation matrix are orthogonal in nature, so you can do this. So that is what is done over here. So it was already in I plus 1th frame. So in previous frame you can calculate by using this. Okay. Okay, so the output of the end effector, moment and force that is specified in the fixed frame are also transformed into the end effector frame using this. Okay, so this was there already, you know. Okay, this is what you have found out, moment, force and the moment. So using Q transpose or Q inverse, it can be converted to the fixed frame which comes here. Now what is this? Q transpose. Rotation matrix Q is extracted from the forward kinematics. That is nothing but the transformation matrix Q1, Q2, Q3. So you have to multiply all of them together so that you can express Q1 to N. Okay, so that is what is this one. So it is product of all those wherever you want to go. So this is nothing but a transformation that takes you from the first frame to the nth frame. Okay, so that is what goes on here. Okay, so that can quickly be extracted from the forward kinematics transformation matrix. It is 3x3 rotation matrix, which is a subset which goes inside to this transformation, homogeneous transformation matrix of the robot itself. Okay, so whatever forces and moments that you get can be converted to first frame by multiplying that to the link transformation matrix, series of link transformation matrix that goes till here. Okay, okay. So now that you know all the link and joint forces and moments, so you now can obtain the joint torque, that is the joint torque. So if you already know the moment, you know moment is a vector that can be projected onto the axis to get the torque. Okay, so projection can be taken by taking axis vector. So EI is nothing but the axis vector. So let me show it in the figure somewhere. So this is your axis vector. Okay, what is that? If you can recall, a transformation matrix has got 3x3 orientation matrix. This shows the position of that frame. This is 0, 0, 0. This is 1, you know. So this is your orientation. The third column, 3 cross 1, this one will tell you EI. If you recall, we have done it earlier. We have extracted all the axis frames and the axis directions using EI, captured that using the column that comes here. So that is what is this for the ith link. Okay, it can quickly be extracted from forward kinematics. So EI. So if you know EI, so if it is a link with a joint that comes here, a joint which comes here, so you know moment which is coming here, you already know the EI vector which is here for the ith link. So moment projected to the axis vector can be a dot product which is there. So it is nothing but a scalar value that comes on to the axis direction. Okay, so that is it. So this gives you the torque value that will go on to the actuator that comes here. Okay, assuming there is negligible friction and other losses, this should be exactly equal to the torque that comes on to the actuator. So this is how it helps in selecting any actuator. Okay, if it is a prismatic joint, you have to convert the force again. Take the projection of forces that is coming there along the axis vector. So axis of the prismatic joint, you have to project that and you get what is again the tau. Same symbol I am using here for the torque as well as force. So it's a generalized torque and force that is there. Okay, where EI is the unit vector along positive joint axis, that is along ZI. Got it? Okay, so EI can be obtained using forward kinematics of the transformation matrix. You know very well now. So yes, so this is how you obtain the joint torque and force, a link moments, what all moments that is going to come, what all force that is going to come on this. So you know all the boundary forces that link sees, including the mass forces that it will see also, if at all Z is acting. Okay, so now you can analyze your body, solid body, which is your link, using all sorts of forces that comes on it. At least the static forces, you know, you can design this link using those static forces at least. Taking factor of safety, it should be quite good enough if your robot does quasi-static job. If it is moving very slow or it is static, so it can be done. Okay, so that's all for today. I think that should be enough to understand the joint torque and force as well as link moments and forces which are there. You can now select the actuator. You can now analyze your link very well. Any further reading, I have suggested a book here which further covers this in very much detail, including the examples. If you are interested, you can go here. For UG, PG and doctoral students who wish to do research and further study in this, to do design of any industrial robot, you should go through this book or any book which is even bibliographed in this book also. So that's all for today. Thanks a lot.